My name is Daniele Mochi. I'm responsible for the K Academy, so the educational program of K-Array, and I'm very pleased to welcome all of you to this webinar, which is the first webinar of our series dedicated to live sound. So let's enter inside one of our columns to see how it's made and why this affects the propagation characteristics of these systems. Because, you know, the market, the professional audio market is full of systems with a self-powered sub and the column, right? But the propagation characteristics of a column depends on what you have inside the column, how the components are arranged, what kind of components you have. And in K-Array, more than 10 years ago, actually almost 20 years ago, when we released our first column, we decided to create a pure line array. Meaning that if you open one of our columns, you will find only a vertical arrangement of closely spaced woofers. That's all. There are no compression drivers coupled to waveguides or horns. There are no passive radiators, no bass reflex ports, nothing. It's only a vertical arrangement of full range woofers. In order to understand the consequences in the propagation properties of these systems, I'd like to quickly review the basic theory of the line array arrangement. Theory that you all know. I noticed that most of you are sound engineers today following this webinar, so absolutely you know how a line array behaves, but just a quick refresh for everybody, maybe also the less experienced ones, right? So here we have a pure line array, so a vertical arrangement of identical, closely spaced woofers. Now, all these woofers play together simultaneously, right? And in point P, I will put a microphone in front of the array. But now, instead of playing all the woofers simultaneously, let's start doing something easier. Let's switch on only two woofers in the array to see how they interact together. And let's play the most simple signal ever, a pure sine wave, like, I don't know, 2 kHz. What's going to happen on the microphone? Of course, we have two sound waves that arrive on the microphone location, and these two sound waves are a little phase shifted, because the green woofer is farther from the microphone than the blue woofer. So the two sound waves are not perfectly in phase, they are a little shifted. But if the two woofers are really close to each other, we can assume that the difference in the two paths is much smaller than the wavelength we are considering. So the phase shift is really small on the microphone location, and as a result the two sound waves are almost perfectly in phase, and the result of the interaction is the red wave, which is 60 dB louder than one single wave. Obvious, that's how two closely spaced sound sources interact. But if now I consider the interaction between two woofers which are not so close to each other, but, for example, in this very example, the green woofer is a quarter of a wavelength more distant from the microphone than the blue woofer, then the two sound waves, the green one and the blue one, will be a quarter of a period phase shifted at the microphone location. And when they interact together, the result is a sound wave that is only 3 dB louder than a single one. If now I consider a woofer that is even farther, to the point where the difference between the two paths is exactly 1/3 of the wavelength, then the two sound waves at the microphone location are 1/3 of a period phase shifted, or 120 degrees, and as we all know, when two sound waves 120 degrees shifted, phase shifted, interact together, the resulting sound wave, the red one, has exactly the same amplitude of one single sound wave. Meaning that if now I switch off this woofer, the SPL at point P is not gonna change. But things can get much worse than having a useless woofer. Because, as we all know, if the difference between the two distances from the microphone is exactly half of the wavelength, or close to half of wavelength, I have a deep cancellation. So this woofer here, it's destroying the SPL that the one on axis is trying to create, of course, at the frequency that we are considering. Then if I go even farther, the two sound waves starts to be again closer in phase to each other, up to the point where the difference between the two distances is exactly one wavelength, and now, again, the two sound waves are perfectly in phase. If I keep going, the next woofers will be again out of phase, and then in phase, etc., forever and ever. So, what happens when all these woofers play simultaneously in a line array configuration? We just said that there is a group of woofers very close to the one on axis, which are all contributing to the SPL at location P. More in detail, we said that this one is giving you plus 6 dB, this one is giving only plus 3, this one is giving plus 0, but at least it's not destroying anything. So these are the good woofers, the one which are effectively contributing to the SPL value at the microphone location. Then we have our enemies, right? The woofers that are out of phase, so they tend to cancel the SPL at point P, but fortunately there are some more woofers in phase, and then some more out of phase, and then some more in phase. So we can say that on average, all the woofers which are not in the first ring of this drawing, they cancel each other out. Because some of them are out of phase, some of them are in phase. So on average, it's like not having them. That's why we usually say when we are in front of a line array, we used to say that we can hear only a few woofers of the column. That's not actually true. We can hear them all, but most of them are not really contributing to the energy that I feel, because they are cancelling each other out. So, at the frequency that we are considering, at the point that we are considering, only the woofers which are now in green are effectively contributing to the SPL level at point P. So, why do we have all the other woofers, if only these ones are really useful? Well, as we all know, that's because as soon as I move farther from the array, the amount of woofers which are effectively contributing to the SPL at my location increases. And this compensates for the fact that I'm more distant. So when I move from here to here, sound should drop a lot because I'm farther from the sound source, but since I have more woofers contributing to the SPL, the sound level stays much more stable. We all know that this doesn't mean that the SPL is constant. But the SPL, if we do a little bit of calculation, we discover that it's going down only 3 dB per doubling the distance, compared to the 6 dB per doubling the distance of a point source. So, one of the most important properties of a pure, ideal line array is that you can cover a longer distance uniformly. But if I keep going away in the distance, far from the array, I'll reach a point in the space where I'm so far from the array that all the woofers in the columns, all the woofers in my cluster, are effectively contributing to the SPL at my location. From this point on, if I go even farther, of course there are no more woofers to add to the line, and so sound starts to drop again, 6 dB per doubling the distance, like an ordinary point source. So I'm so far that the line array starts to behave actually like a point source. We can see it pretty well if we do an acoustic simulation. This is a side view, and you can see on the left a pure line array, one of our columns, 1 meter long. And you can see this is a simulation at 2 kHz, which is a very important frequency. 1 octave around 2 kHz is where the clarity is, so it's a good frequency to study. And you can see that up to 8-10 meters, the SPL at these frequencies, it's pretty stable. Then it starts to drop quickly. Why? Because we reached the distance where all the woofers are already contributing, and so if I go even farther, there are no more woofers to add, because the column is only 1 meter long. But if I join together 2 columns to create a 2 meter long array, now I can throw the beam much farther. 1 meter, 2 meters. And if it's not enough, I want to reach a distance which is longer than 20-25 meters, no problem. I join 2 more columns and I create a 4 meter long array. And now I can easily reach 60 meters with extremely high intelligibility. Again, 1 meter, 2 meters, 4 meters. This is how a pure, ideal line array behaves. So, now it's pretty obvious that if I'm doing a live event in a small bar or venue, which is like 10, maximum 15 meter long, a column which is 1 meter long is more than perfect to cover it. So our system KR102 is the perfect choice. But if I have to cover a longer distance, and in this stadium they had to cover for sure a longer distance with our columns used to reinforce the Asian Games opening a few years ago, I'd better go with 2 meter long columns, so that I can throw the beam more in the distance. But I could also decide to suspend the columns and leave the subs on the ground, so that suspending the columns it also helps to send the beam exactly where it's necessary, and all our columns can be easily flown with a dedicated flybar. So if you have one of the systems like the Pinnacle KR402, you just buy 2 flybars accessories, and then you can fly the columns and cover. You see, this is a pretty large venue outdoor for an opera event in this case, or a big theater. And here, actually there is, if you notice, one Pinnacle KR402 system used as a side field, so monitoring of the whole band and orchestra on stage, And then there is the PA system, in this case left, center, and right, with KR802 Pinnacle Systems, where the subwoofers are left on the ground and the tops, the columns, are suspended. But it's here that really the fun begins, because if you have to cover an even larger venue, or you want to cover a balcony or two balconies and the first rows as well, so you need to distribute the beam in a larger venue, you can easily merge together two systems, like two Pinnacle KR802 systems, to have 4 columns per side. And now you really can throw far. You leave the subs on the ground, and as I told you, the subwoofers are self-powered and they are driving the columns, but on the sub there is a 2-channel amplifier, so the columns and the subwoofers are independent. You can delay them independently with the onboard DSP to realign, for example, the subs and the tops in this example. The columns can be easily joined together with the included hardware, and you can set from -10 degrees to +10 degrees the angles between the columns, so to shape the array the perfect way to cover the whole venue. And something that I like a lot about this event is that they used also actually half of a Pinnacle KR802 as a front fill. Why not just dismounting the 2 columns and using them as a front fill? Again, powered by one of the subs that is there in front, and since you can delay the columns independently from the sub, you can of course use the system also for a front fill in this case. So the concept is that if you are a rental company and you have several of these systems in the warehouse, like 3-4 Pinnacle KR802, one day you can use each of them in a different venue. So you have 3 events simultaneously in the city, you use the 3 systems. When you have a bigger event in a larger space, you just merge together all the systems to create a longer PA, to add a front field, a side field, monitoring, still using the same exact systems that you already have. Same example, 4 meter long per side, so Patti Smith concert in large theaters, and again, you can see the example of merging together 2 of these systems to create a larger one. But covering a long distance uniformly is only one of the main features of a pure line array. All of you know that another characteristic of a line array is the high directivity in the vertical plane, the ability to focus the beam on the vertical plane. How can we explain that? Well, it's pretty easy, actually. If we go back to our picture where we have our microphone, and we already said that only a few woofers in front of the microphone effectively contribute to the energy at that location, what happens if I move off axis? Well, here I'm still, let's say, inside the column, and I'm still in front of the same amount of woofers, so I'm not expecting a big SPL variation from here to here. But as soon as I seriously move off axis, like here I'm at the top of the column, of the cluster, now the number of woofers that are effectively contributing to the SPL at my location is strongly decreased, and so will be the SPL from here to here. And if I go even more off axis, we all know that sound will be strongly reduced. Then there will be some secondary lobes and other things, but mainly you have a very strong reduction of the SPL of axis. And this is extremely important, for example, in a theater, where you want to avoid sending energy towards the ceiling of the theater, which is usually one of the most reflective surfaces that it's creating reverberation. So having a focused beam is something that absolutely helps. And it helped also on this cruise ship. This is the Costa Victoria cruise ship, where the system has been permanently mounted. So in this case they bought some wall brackets of ours to permanently install the system. The subwoofers are under the stage, and in these cruise ships, like most cruise ships, there are some bedrooms above the event area. And with the previous system, that was more kind of a point source approach, people were complaining from the bedrooms during live events. And now that they have a system that is focusing the energy on the vertical plane, of course, you cannot hear the voice of the singer while you are sleeping above. And that was absolutely an advantage in this specific application. What about the horizontal plane? Because we said, okay, high directivity in the vertical plane. In the horizontal plane, instead, our columns are extremely wide. Why is that? Because, of course, on the horizontal plane there is no array arrangement. It's just a single small woofer. And so the polar pattern of these systems, as you can see, is narrow in vertical and wide in horizontal. And this picture, I think, explains this very well. I don't know if you can see the cluster, but it's here, right in the middle. 6 columns joined all together in a mono hang. In this case, the system was used for reinforcing the voice of the singers, so they didn't need it in stereo, they went mono, and thanks to the wide horizontal coverage of the system, the theater was completely covered with just this slim line of speakers, which are so discreet that even if they are in front of this beautiful organ, you hardly can spot them. This is another picture that I think kind of sums up what we have talked so far. What happens if you decide to put 2 columns side by side instead of one on top of the other? Well, of course, you decrease the distance that you are able to cover uniformly. You decrease the throw of the beam, because it's a shorter array, right? But at the same time, since you have 2 columns mounted, you double the SPL. So in this case, they didn't have to cover a long room, so they decided for this Red Bull event to go with 2 columns side by side to increase the SPL and reduce the throw of the array. Last but not least, we have been talking about one single frequency in all our examples, like the 2 kHz, but actually our line arrays are reproducing a very wide frequency range. So, what happens when all the frequencies are reproduced by the array? Well, in this example, we are back to 2 kHz, so we know it, right? At the location P, we only experience the energy of a few drivers, a few woofers, inside the ring in the drawing. If I stay in the same point, So same location, same distance from the array. But I consider a lower frequency, so a longer wavelength. The amount of buffers which are coupling constructively at my location increases. 2 kHz, 500 Hz. So, as a consequence, and as you can see from the simulated frequency response, there are more buffers contributing at 500 Hz, so you have more energy. And is this a problem? Is this a problem that at 500 Hz I have more energy than 2 kHz? Usually not, because actually we want some punch in the mid-lows. But sometimes, especially when you deploy long arrays and you switch them on, you feel that the sound is a little dark, like some high frequencies are missing. And some people may wonder, it's a problem in the preset, is something wrong, why it's so dark? No, it's the physics of the array that works this way. If a long line array is too dark, you can just use an equalizer to reduce a little bit the mid-lows. That's what I usually do, especially when I have like a 6 or 8 meter long line of cabinets, right? So absolutely no problem. The real problem here is that now, if I go even lower in frequency, so I consider, for example, the 250 Hz in this example, the wavelength is so long that all the buffers available in my cluster are already contributing to the energy at my location. Meaning that even if I'm still pretty close to the array, I'm already in the so-called, I'm already above the critical distance. I mean, the array is already behaving like a point source at this frequency. When we say that we use line arrays, we need to have in mind that a line array behaves like a line array, so a narrow coverage in the vertical plane and long throw, only for the frequencies, only from, let's say, some frequencies up. Because the lower frequencies, if the array is not long enough, it's impossible to really throw them in the distance. But if you create a long array, like 4 or 6 meters, now you can really throw even the mid-low frequencies in the distance. And you can really control the beam and avoid sending too much energy on the ceiling, even at low frequency. That's why I really encourage everybody to create long arrays. And with the Pinnacle series, it's extremely simple, because it's only a matter of combining together more systems to create a larger one, or I'd better say a longer one. Because that's what we need to have full control on the beam in the whole frequency range reproduced by the system. In a place like this is the Lincoln Center in New York City. Instead of deploying a lot of short, small line array elements all around, much better to go with 6 columns per side, so 3 Pinnacle KR402 systems, in this example, merged together. And then really you'll have a high intelligibility even in the farther seat from the array. Same in this beautiful theater, this time in Italy, the Teatro alla Scala in Milano, one of the most famous opera theater in the world. And again, same approach. Self-powered subs on stage or under the stage, and the columns all joined together at the size of the proscenium. So, the unique propagation characteristics of these systems are based on the fact that they are pure arrays, only identical, powerful, full range, closely spaced buffers arranged in a line. And you can join together many columns to create a cluster with the length that you need for that specific event.